Hi, I'm Alex Manassa from Prometheus Education. Today we are going to do a tutorial on how to breadboard like a professional. We'll be using materials for this lab, so please see the description for the full list of materials and where to buy them. Breadboards, or solderless prototype boards, are for testing circuits rapidly. You can go from an idea to a working circuit within minutes. All circuits are made by just connecting electrical components together by physically connecting their conductive terminals. A solderless breadboard allows you to connect circuits by inserting them into these holes. Each hole has little lips inside which grip onto the electrical leads. Here we see a naked breadboard. So I've stripped off the back of this breadboard so we can see the terminals inside. Pardon all the goo. This is from all the double-sided adhesive tape that's on here. So let's get in there and see what's inside. Okay. So inside we have these little lips in each of these rows, and these little lips grip onto electrical components like resistors, LEDs, anything with a lead on it. Okay, see that? All right. Let's go ahead and put this guy back in here. All right. So we can easily see from this how the breadboard is connected internally. You have holes on the left side and on the right side of the board, but each hole has these rows. These 5 holes here, these sets, all connect together. And that's how we're going to rapidly connect all these circuits together. Oops, let me get that back in the view. So we can identify each of these rows by both the number and the side that it's on. So for example, you might have 20 left and 20 right. You'll also notice that there are these rails that go along the entire length of the breadboard. These are usually for power and for ground. The red is for power and the blue is for ground. Now, red power is usually, that means it goes to the positive voltage of the power supply that you're using. The blue is going to go to the lower voltage of the power supply you're using. So that's where we get power and ground, the word power and ground from. So now that we've seen how the breadboard's connected internally, we're going to take a look at some breadboarding techniques. So over the 10 years that I've been doing electrical circuits, I've come up with 5 main rules for making a breadboard professional. So we're going to demonstrate these 5 rules by making this circuit here. So this circuit here is actually a light sensing circuit. It may not look like much, but this circuit converts the number of photons into this little sensor right here into a voltage. So that voltage we can be read by a multimeter, an oscilloscope, or even a microcontroller. And there'll be tutorials later on to show how to connect a microcontroller to the circuit. So let's go ahead and get started. Let's go ahead and grab a blank breadboard here. Get that aligned, get it centered. Very nice. Let's get this Duracell out of here. You never want to have power applied for longer than you need it to be. Okay, straighten out. Okay. So, rule number 1 for breadboarding. Always insert leads so they go straight down into the board. So, for this rule, we're going to demonstrate with a 10 kilo ohm resistor. If we want this to go straight down, if we want these leads to go straight down into the board, we're going to have to bend them using a tool called a flat-nosed plier. So these flat-nosed pliers are great for grabbing onto something without marring the surface or without damaging the component. And you just grip right at the point where you want to bend it, like so, and then just seat it right down. So nice and gentle, nice and easy. Grab the other side. Nice and easy, nice and gentle. Alright. Now this brings us to rule number 2. Rule number 2 states that we should not leave more than 1/4 or much less than 1/4 of an inch of lead to engage the breadboard. So we estimate about 1/4 of an inch, trim it off, set the remainder to the side, trim it off, set the remainder to the side, and there we go. Now, if you have more than 1/4 of an inch, the component's going to stick out of the board too much and it might fall out. Have less than 1/4 of an inch, you're not going to get full engagement, and it'll also possibly just fall out. So let's go ahead and insert this into the board. Let's say we'll insert it, put this backwards. Let's say we'll insert it into 20 left and 17 left. So position it using a tool known as right angle tweezers. Let's position it into column D so we have some room for other components later. Place one lead into row 20 left. Use your finger to gently bend the leads where you need to go, and voila. The tweezers are there for placing the part, and then your finger is there to apply pressure to push the part in. If you're having trouble pushing the part into the breadboard, try jostling one of the leads with the tweezers and then trying again. You shouldn't have to use a lot of force to get components to go into the breadboard. So that's rule number 1 and rule number 2. Rule 1, parts go straight down into the breadboard. Rule 2, only leave about 1/4 of an inch. So here we have a different package. This is the photoresistor. This package is radial, and I can get into what that means later, but that means that the parts are going to come out in one single direction or two different directions that are not the same, along the same axis. What we have to do for this part, grip it where you want to bend it. So I'm going to bend it like this, gently turn it over. There we go. Okay, we're going to stick one leg out to the side like that. Grip it again. Stick one leg out to the side like that. We're going to put this between 17 left and 17 right. So I'm going to put these side by side and just estimate like that. I'm going to grab the other side just like that. Perfect. So this should satisfy rule number 1. We're going to be able to place this down into the board. Now, we only want to have 1/4 of an inch of engagement here, so let's take our wire cutters. So these wire cutters are special. These are called flush cutters. They're great because they leave a clean edge when you cut. They're also good for precision, so they just give a little snip there. Okay, I'm going to use my tweezers to do this. One lead in, another lead in. There we go. Very nice. Okay. All right. Here I am getting myself together. So there we go. All done, looking quite professional. Now all we have to do now is connect this lead over to power and this lead of the resistor over to ground. Why we're doing that, we can explain in a later video about electricity and how it flows, but really we just need electricity to flow from power to the photoresistor, down to the resistor, and then through the resistor down to ground in what's called a voltage divider. Now if you want to just Google voltage divider and learn how those work, that's perfectly fine. So we have one more thing we have a few more things we have to do actually. So rule number 3 is that we don't cover more holes than we need. So we could take one of our jumper wires from our jumper wire kit and connect power, here we go, connect power to 17R right here, but we've needlessly covered this extra hole right there. So we don't want to just cover that hole, we might need it later. We're going to take this out, grab an appropriate length, appropriately length wire, place that instead. So rule number 3 is there so you don't accidentally, what they call, paint yourself into a corner. Your circuit's going to start growing and growing and growing on this board. It's going to take up the entire thing eventually as you build more and complex circuits. You want to leave yourself as many options possible, and if you cover a hole, you've just covered an option that you have. Keep your options open as you go forward. We're going to take another wire here and connect this resistor over to ground. So use the tweezers to maneuver the part into the hole. Use your finger to press it in. Very good. Now what we have left is this wire here. So if we pull out the internals of the piece got stuck on there. If we pull out the internals of the breadboard again, we see that there's nothing actually connecting one set of rails to the other side of the board. We're going to need some resistors here to go ahead and jump those sides together. Now, this brings us to rule number 4 and rule number 5. So rule number 4 is to bend everything at a nice, tight right angle. This allows you to see more easily where things are going. The alternative to this would be as if you just had loop-de-loops. These nice right angles keep everything really neat, and they also keep your circuit from snagging. So it actually takes a little bit of effort to snag this. If you have a loop, they're prone to just come right up off of the board a lot more easily, and those will snag. We also have rule number 5. Rule number 5 is to keep everything flat to the board. You don't want anything sticking out at all, because of course you'll snag again. So we're going to take a wire, connect ground to ground. I don't want to cover any more holes than I need to, so I'm going to go around these holes at the bottom, jump from ground to ground. So using your pliers, just estimate the path, grab the part you want to bend it. Again, grab the part you want to bend. Right about here ought to do it. It's a bit awkward angle, so you can get around here. There we go. Okay. So now we've got a nice right angle bend. I'm going to use these tweezers now to just mark in the insulation where I need to cut the wire. And about 1/4 inch from that is where I'm going to snip. So using my flush cutters, go ahead and just snip that. No, didn't come off all the way. Okay, snipped. And I'm going to use my final tool for the day. It's a pair of wire strippers. Let's get ourselves centered again. Pair of wire strippers here. I'm going to take the wire out right where I marked it with the tweezers. I'm going to put it in the size 20 slot because it's a 20 gauge wire. I'm just going to twist it in there a little bit. Okay, come on. Give it a little rattle in there too. There we go. Now we snapped it. Very nice. While this is out, I'm going to go ahead and straighten ourselves up. Okay. This needs to bend straight down. It has done so. Let me make this a little bit less curvy. There we go. And looks like I have a little bit of excess here, so I'm just going to go ahead and snip the wire. Now we're the perfect length, so not too bad. A little bit of fuss, a little bit of muss, but now it's out of our way. We have all our options open still, or at least as many options as we can, and this thing will not snag too bad. I'm going to do the same thing with this orange wire here. So grip it where you want to bend it up. Actually, I'm going to take it out of the board. Bend it up like that. Okay, let's put it in here so I can estimate where I need to bend it again. It's like right there, bounce. Okay, very good. All right, take this out of the board. Oop, dropped it. Bend this upward. It's an ugly process, but comes out looking quite good in the end. Okay, bend that down. Very good. Estimate about 1/4 inch is right about there. Okay. My snips, sorry, with my wire strippers, put it in, give it a little twist and rattle around in there, and twist it, and it should come nice and clean. snip off the excess wire right here. Sometimes the stripping process can be pretty traumatic for the wire, so you just have to straighten it back out again. Some people might think these, what do we have happen here? We got some bad stuff just happened to this thing. Yeah. I think I stripped it at the wrong point. Let's do it again. Some people might say that the right angles will cause a reduction in the fatigue life of the wires, and this is absolutely true. But how often do you really need to be doing this? Hopefully you don't have to bend and work with these wires too often or use them too often. Wire's pretty cheap. What's not cheap is your time, and time spent re-looking at your circuit to the side and trying to figure out where things are going. That's time wasted. You don't want to waste that time for sure. Okay, I think the length got goofed a little bit there, but it's not too bad. Let's just press that down. Yeah, I could do a better job of estimating the length, but normally you take your time with this. I don't want to use up too much of your time estimating these lengths. Okay, so now we have this full circuit. So here's our example here. The last thing we have to do is just remove the power and ground of the battery here and insert them into the power and ground of our new circuit. Perfect. Okay, so I'm going to get rid of the example now because it's in fact even less complete than our current circuit here. Place the 9-volt battery right on there. Let's get that off to the side. Looking good. Looking good. Very nice. Now let's see the circuit in action. So here we have a small oscilloscope that I've soldered together, and we have our battery in place, and we're probing across this resistor. So what the circuit does is it measures the amount of light. So if I take my hand and I just block the little sensor guy right here, you'll see the light begins to drop. There you go. If I dark it out completely, just put my finger right over top of it, it goes down about this level. There you go. And that's how you convert, within like $1 or so's worth of components, that's how you convert light into an electrical signal that you can then measure. So now let's go ahead and remove the battery so we can continue working on this circuit. We have one last thing we want to do. It wouldn't be an electronics project if we didn't light up an LED. Let's go ahead and remove my probes. Okay. So, clean off my work area here. Before you start working with an LED, you have to know what's inside. So I've cut out an LED here and put it right on this. You can see here that there's a bit of an asymmetry inside of the LED window. You see that one side is larger than the other. The larger side is over here, whereas the smaller side is over here. The smaller side is called the anode. The anode is what we want to connect to power. The cathode is the other side. The cathode is what we want facing towards ground. We're going to make our circuit so that it goes from the red rail to this anode. Then the cathode is going to go to a 1 kilo ohm resistor and then to ground. So to do that, we'll take a single LED, grab our trusty flat-nosed pliers, identify the anode, and I want to bend that anode straight out. Now, there we go. There we go. Straight out there. Go ahead and estimate a small amount of length here. Bend it down just like that. So now that's our LED. Don't forget rule number 2. I want about 1/4 of an inch of lead to engage with the circuit, or to engage the breadboard here. So I'm going to place that here. I have already preformed a 1 kilo ohm resistor right here. Feel free to pause the video and try lead forming your own. Remember, 1/4 inch of lead length to go into the breadboard, and bend the lead so they face about straight down. So let me squeeze this one a little bit. Using my trusty tweezers. We're going to go into ground. Oh. So the tweezers are good for positioning it. They're not good for pushing it in, so you have to use your fingers for that. Try to push it in evenly on both sides. That way you don't get one side sticking out and the other side pushed all the way in. You want to push it all in together as a unit. Lastly, I'm going to take this 1/10 of an inch jumper and connect the resistor and the LED together. Again, using the tweezers. Jostle it into place. My finger should be able to just lightly press onto that. Get it connected. Take our 9-volt battery. I always do this visual check with a 9-volt battery because if I touch these two, it'll all be in reverse. This circuit we have here is not going to get damaged by reversed voltage, but it's good to just never apply the reverse voltage to any of your circuits. So now we're going to go ahead and connect the 9-volt battery. Voila! We now have light. So here we go. No microcontroller project or no electronics project would be complete without an LED turning on. So that's our circuit. We have a light sensor. We have an LED. Now, with this, I'm going to nerd out here for a second because this brilliant green glow means you've did good. That's 569 nanometers of success right there. With a resistance of 1 kilo ohm and a typical forward voltage for this diode of 2.1 volts, this 9-volt battery will put through about 6.9 milliamps of current through the LED. This equates to just over 43 quadrillion photons per second coming out of this LED, assuming there's 100% quantum efficiency. So this, by the way, this is the number of photons coming out per second. So to give a sense of scale, a single quadrillion is about the number of stars in the entire Andromeda galaxy. If you thought of every photon out of this LED as a single star, there would be 43 Andromeda galaxies worth of stars coming out of this LED every single second. So photons, lots of them. I hope you enjoyed this video and I hope you learned a lot. If you want to see more of these videos, please hit subscribe. I'm not sure what the like button does yet, but I guess it gets more attention on the filters in YouTube. Feel free to like it if you like it. If you don't like it, then don't like it. Hope you learned a lot again, and this has been Prometheus Education and Alex Manassa. I will see you next time. Thumbs up. There we go.